Hi. So yesterday we talked about infinite sequences. So you had a sub n in these brackets, which meant a sub 1 comma a sub 2 all the way up to a sub infinity. It never stops. So today all we're going to do is take the commas away and add plus signs in between them. So we're going to make a1 plus a2 plus a sub n, and it keeps going on forever. So we're going to write that as a summation from k equals 1 to n, or 1 to infinity of a sub k. So we're just adding up all these starting at 1, and again, just like with sequences, it doesn't have to start at 1. That's just a normal place to start it. So this is going to be called an infinite series. And then we're also going to define, that's just a definition, then we're also going to define a partial sum, S sub n. And all a partial sum is adding up the first n terms. So this would be a sub 1 plus a sub 2, just stopping at a sub n. So you could write it instead of going from 1 to infinity, you just go from 1 to n. And then we can say, because we're going to be interested in whether these series converge or not. So we're going to say, if the limit as n approaches infinity of S sub n equals some number s, then the series k equals 1 to n of a sub k, that infinite series, converges to s. Otherwise, it diverges. So basically what we're going to do is we're forming a new sequence. S sub 1, S sub 2, S sub 1 is adding up just the first term. S2 is adding up the first two terms, and you keep adding them up, you keep getting different values of S that form a sequence. It's going to be S sub n. And we're going to just take and see whether this sequence converges to some number s. If it does, we say that's what the series converges to. Otherwise, it diverges. So, let's just take a couple of examples. Here's one right here. K equals 1 to infinity. So when k equals 1, you get negative 1. Then plus k equals 2, you get 1. Then when k equals 3, you get plus a negative 1. K equals 4, you get plus 1. And you can see that this is just going to keep going on. So if you looked at the first partial sum, you're just get negative 1. If you look at the second partial sum, it's negative 1 plus 1, or 0. S sub 3 is going to be adding the first three terms, and you can see that this sequence is going to be negative 1, 0, negative 1, 0, and it's just going to keep doing that. So is the limit as n approaches infinity of this sequence converging to something? And you can see it isn't. So because of that, I can say this series up here diverges. It doesn't converge to some sum. Two different sums. Okay, let's try one that might be a little less obvious. This one you could kind of see was not going to converge, but this one is a little bit harder. So if you put in k equals 1, you get 1/2. Then if you put in k equals 2, you get 1/6. If k equals 3, you get 9 plus 3 is 12, so 1/12 plus 1/20, and then it keeps going. We might want to see, does that converge to something? And if it does, what does it converge to? Well, it's a little hard to tell, but we're going to use a little trick that we did when we did partial fraction decomposition, or Jackson 5, when we were doing integrals. We can break this fraction up into two different fractions. We can make it a over k plus b over k plus 1. And then if we put them back under the same denominator, I want that to equal 1. So when k is 0, I get a equals 1. And when k equals -1, I get b equals -1. So I can take this fraction up here and make it into two separate fractions. 1 over k, and then minus 1 over k plus 1. So now, if you look at the series, what do you get? You get 1 minus 1/2. And now when k is 2, you get 1/2 minus 1/3. Then you get 1/3 minus 1/4. And this keeps going. So what happens is, if you look at the nth partial sum, what are you going to get? You're going to get these are all going to add up to 0. So you're going to get this first 1, and then at the very end, on the nth term, you're going to get 1 over n minus 1 over n plus 1. That 1 over n plus 1 is going to be left over. Everything else in between will add to 0. So that's the nth partial sum. So we can go back to here and take the limit of this sequence of partial sums. 1 minus 1 over n plus 1, and we know that this is going to go to 0. So basically, we get 1. So we found out that this converged to 1. We had to use a little bit of a trick, but we were able to do it. Okay, so let's try this one. Starting out with n equals 1. A is representing some constant, and r is representing some constant. And so when n is 1, you get ar to the 0, which is just a. Then when n is 1, or n is 2, you get ar. And then you get ar squared, and then it just keeps going. This type of series has a special name. It's called a geometric series. Because every term, you get to the next term by multiplying by the same thing, r. So a times r squared. You're multiplying every term by r to get to the next term. That's referred to as a geometric series. So let's look at what S sub n is. It's a plus ar plus AR squared plus AR to the n minus 1 plus, well, when it gets to n, you're just going to be up to there. Now let's multiply every term of this by r. Now, a times r is ar. Then you're going to get ar squared. And when you get to this term, it's going to be, you're going to get an ar to the n minus 1, but then the last term is going to be ar to the n, because you're multiplying this last term by r. Now, if I take these two things and subtract them, I get s sub n times 1 minus r. And if I subtract these, look at everything in here goes to 0. So I'm left with just a plus ar to the n, or a times 1 plus r to the n. And then if I just divide by 1 minus r, I've got what my nth partial sum is. So to find out if it converges, I take the limit as n approaches infinity of my nth partial sum . So it's all going to come down to this. Everything else is just constants. So what do I know about r to the n? Well, if r is greater than 1, then this is going to get ridiculously big. And so it's going to just go to infinity. It's not going to converge. So then we could say the series diverges. But if r is less than 1, then you have a fraction to the nth power. As n approaches infinity, that's going to go to 0. So this is either going to go to infinity or it's going to go to 0. Well, if it goes to 0, what's left? A over 1 minus r. The series converges to, and we even know what it converges to, a over 1 minus r. And this is going to be the same thing if r happens to be a negative number. A negative number to the nth power is just going to get really huge, so it's going to diverge. So we can really say in absolute value. The same thing for negative numbers. So the only thing we haven't looked at is what if r is 1? Because I can't divide it by 0. Well, but if r is 1, you just get a plus a plus a plus a plus a, which obviously doesn't converge. So we can say greater than or equal to 1. So this geometric series always converges if r is less than 1 in absolute value. And it always diverges otherwise. And if it does converge, we have a formula that we developed to do that. So that's going to be pretty important. In general, it's not going to be so easy to find the nth partial sum. Even this was a bit of a trick. And this was a bit of a trick. So in general, we're not going to even be able to find out if infinite series converge, or at least what they converge to. So what we're going to try to do is find out if they converge at all. And that's going to be a really important question, as we're going to find out a little bit later. So we're going to come up with a series of tests. And I'm just going to do maybe the easiest one, and always the first one you're going to try to see whether an infinite series converges or not. And this is actually called the Nth Term Test, or the Divergence Test. And it says basically, if the limit as n approaches infinity of a sub n does not go to 0, then the summation k equals 1 to n, or 1 to infinity, of a sub k diverges. And that's why they call it the divergence test. Because if you can just take the series and look at the nth term of the series, and that term does not go to 0, we can say automatically that it diverges. And if you think about it, it makes some sense. Because if these terms, even if they're getting really, really small, if they don't go to 0, say they go to some really, 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 really small finite number, instead, you're still going to be adding that to s sub n when you're looking at the sequence of partial sums. So s sub n is going to keep getting bigger and bigger, even if it's by a small amount. Since you're going to infinity, it doesn't really matter. It's going to keep getting bigger. It's never going to converge to a number. So this theorem kind of makes a lot of sense. Now, the question you might ask, does it go the other way around? Is this if and only if? In other words, what if the limit does equal 0? Does that mean the series converges? Well, I've already shown you an example of what do you get when you have 1/2 plus 1/4 plus, well, let's see, 1 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8, and you keep going. This would be for the series 1 over n. Maybe I'll even put a 1 in front of it. So then I can go from n equals 1 to infinity. And I showed you when we were doing improper integrals that 1/2 is a number. If I take 1/3 plus 1/4, that's bigger than 1/4 plus 1/4. So this that I circled is going to be greater than 1/2. And if I keep doubling the things, if I take now 4 things and add them together, 4 of these numbers in the series, all of these numbers are bigger than 1/8, except for that one, which is equal to 1/8. So this whole thing is going to be greater than 1/2. So you can keep accumulating by doubling the number of terms you take, you keep getting these groups that are bigger than 1/2. So you can see that that diverges. So this only goes one way. We can look at a series and see if the nth term approaches 0. If it doesn't, we say it diverges. If it does go to 0, we just have to keep looking. The test kind of fails to some degree. Okay, so now I'm going to go to the other board and we're going to just look at a few examples from what we've done so far. We basically have 2 things. We have the geometric series and we have a test now for all series, but we only have 1 test. So, find out if the following series converge or diverge. And if they do converge, find out what they converge to if possible. This is going to be a little bit easier than it is going to be a few days down the road when we have more tests to look at. But right now, I look at this and see, what does my a sub n term look like? Well, it doesn't even have an n in it. So every term here is going to be the same. That's what you get when n equals 0. That's what you get when n equals 1. So the limit as n approaches infinity of this n plus first term is going to be that. It's not 0. So by the nth term test, I can say this diverges. Even though the terms are really, really, really small, we've got all the way to infinity to keep adding these up, and so they keep accumulating. If you get enough of these together, they're going to accumulate to something of value. So we use the nth term test to show that that one diverges. Okay, this next one. I think if you use your ideas that this is a summation, and we can use all the rules that we always learned in summations, that we could break this apart into two separate summations. When we're adding up numbers, it doesn't matter the order that we add them up. So I can make this 2 over 5 to the n plus 3 to the n over 5 to the n. And I can make this 2 over 5 to the n. And also, you can factor, when you're adding things up, you're allowed to factor things out. So I could bring the 2 right out front. And if you look at these closely, what we have is geometric series. So this first one is 1/5 to the n, and the other one is 3/5 to the n. So they're both geometric series. They're both AR to the n. Now, it's important what the first term of the series is. We're starting at n equals 0. So the first term of this series is going to be 1. 1/5 to the 0 power is 1. So I can take 2, and the formula we learned was the first term over 1 minus what r was. So that formula that we learned, that if you have AR to the n, the sum is A over 1 minus r. And the same thing for this one. This time we have A, the first term is 1 because we're starting out at 0, over 1 minus 3/5. So 1, this is 4/5, so you're going to get 5/4. And this is 1 over 2/5, so you get 5/2. So you get 5/2 plus 5/2, or 5. So this series up here, not only we know that it converges, but it converges to 5. Geometric series are going to be kind of special in that we can, with a formula, figure out what they converge to. Okay, this next one. Pi and e are both numbers. So pi over e is just a fraction. So again, we have a geometric series. It's r to the n. But what do we know? We know that pi is bigger than e. So this fraction in here is bigger than 1 in absolute value. So all I have to do is say the series diverges. You could also use the nth term test, but I think it's easier just to say it's a geometric series with r, which happens to be in this case, greater than 1. If it had been the other way around, e over pi, then we could have actually figured out what it was. Okay, coming to the next one. It's certainly not a geometric series. And I just started at 12 instead of 0 or 1. It doesn't really matter where you start as far as convergence is concerned. The first 1,000,000 terms don't really matter. It's what happens after that that really matters. So what do we see though? We know from our knowledge of the sine function that the denominator is always less than or equal to 1. And the numerator keeps getting bigger and bigger and bigger. So we know that this term right here, we can say the limit as k approaches infinity, the square root of k over the sine of k is not equal to 0. In fact, it's going to go to infinity, but the key was these terms that you're adding up are not equal to 0. So you can say by the nth term test that that series diverges. Okay, so here comes another one. And I think one thing that will make this easier, if you take this constant, you don't have to do this, but if you take that right out front, that makes life easier. And sometimes it's even good to write out the first couple terms. So when n is 0, what do you get? E to the 1 over 3 to the 1. E over 3. Then when n is 1, you get e squared over 3 squared. And it keeps going forever. So again, we're seeing a geometric series. To get from this term to this term, you're multiplying by e over 3. If you rewrote this, it would really be e over 3 to the n plus 1. That's like having r to the nth. It's a geometric series. And e is like 2.7 point something, so r is less than 1 in absolute value. So we know that it converges. And we can find out what it converges to. It converges to a, the first term, over 1 minus r. And r is e over 3. So that would be your answer. Now, those of you who don't like fractions within fractions, I don't blame you. You can multiply the numerator by 3 and the denominator by 3. And you can get something that looks a little bit nicer. So we can say that that series converges to this number. Okay, well, look at this terms. These terms are so small that I must converge. What's the first term going to be? When n is 2, you get, let's see if I've got enough. You get a 0.02 over 1,000,002. Don't you think that's so small that it's going to converge? Well, you could be fooled by that. But realize, what happens if you take the limit as n approaches infinity of this number? Remember, as n approaches infinity, we can ignore everything in here but the highest power of n. We can ignore the 1,000,000. And what do we get? 0.01. So the terms are converging to 0.01, and that's not 0. So even though it looks like maybe that was going to converge because those numbers are so small, eventually, as n gets big enough, then the 1,000,000 is actually not going to have much effect at all. And all these fractions are going to be really close to 0.01. So by the nth term test, the series diverges. Okay, so let's just end with a word problem. So this one says, start at the point 1, 0 as the rightmost point of a circle. Make circles with diameters equal to 1/2 the distance between the starting point and the y-axis, and find the total area of the circles. So 1/2 way between here and the y-axis would be at 1/2, and I'm going to make a circle with that diameter. And I have to find out the area. So what's the area going to be? Pi times the radius squared. Well, the radius here is 1/4. And now we go 1/2 between this point, so right at 1/4, we're going to make another circle. And what's its radius? Its radius, since this total distance here is 1/4, it's going to be 1/8. And then let's try one more. Now you're going to go to 1/8. So this is going to be 1/16 squared. And you're going to keep going and you're going to make circles forever. But they keep getting smaller and smaller. So basically you're adding up an infinite number of circles. Well, that's like an infinite series. So what do these terms look like? Pi times 1/16 plus pi times 1/64 plus pi times 1/256. You can see to get from this term to this term, you multiply by 1/4. The same thing here. So we take, this is a geometric series, and the first term is 1/16 pi, and r is 1/4. So the answer is going to be pi over 16 divided by 3/4 or times 4/3, and you get pi over 12. So even though there's an infinite number of circles, we were able to figure out their total area. And it's not even very big. It's only pi over 12 square units. So anyway, that's our start on infinite series. We will learn on the next 3 talks more about whether we can find out if a series converges or diverges with other tests. So until then, take care.